We're now going to take a look at another method for calculating volume, and this method is specifically referred to as the shell method. Now, the key learning objectives of these next several videos is we want to find the volume of revolution using obviously the shell method, and I want to make a comparison between the disk method and the shell method. There are times when the shell method is so much easier than disk method it just blows your mind, and other times the disk method is definitely the way to go. So let's start off by developing the idea of the shell method, where it comes from, what this thing's all about. So first I'm going to draw a picture, and then we'll talk about what's written up here and connect the dots here. Okay, so I have some function along the xy axis. Maybe it looks something like this. And I'm going to take this thing and I'm going to revolve it about the y-axis for sake of this discussion. Now when I do that, obviously when it goes around the y-axis, I can look at this as breaking this down into pieces, and each piece can be a rectangle. So if I think of a rectangle slicing this right here, then this little piece right here is really nothing more than the rectangle going all the way around this axis of revolution, the y-axis in this case. And obviously, if I make this rectangle infinitely small and think about moving it all the way from, let's just say A to B for sake of discussion, then what I would have is actually the total volume that's represented down here that's spun around the y-axis. So I'm going to think of the width of this rectangle as W, just for notation purposes. The height of this rectangle as being H. And I'm going to pick a spot right in the middle of the width here, right in the middle of the width of the rectangle. And I'm going to call that distance from the middle of the rectangle to the axis of revolution as being P. So if I concentrate on just a moment on nothing but this rectangle, actually I should have drawn it that high, this rectangle right here, I'm going to think about just that rectangle for a moment. Let's just say that here it is. And if I'm revolving just this piece about the y-axis, then what I'm going to get is something that kind of looks like this. And this is some type of solid. It's a ring is what it is. Actually, I should probably draw a little bit more like this. We get this ring. And this ring is what I'm thinking of as a shell when I'm talking about the shell method. So what I really need to do is try to figure out how to find the volume of really just that ring. Well, if I tip it on its side and look at it like this, now let me see, let's make that a little bit bigger. Now this is like the top of this ring right here, and I have the axis of revolution going through here. So this has some depth to it. Now this distance here is the same as this W that I wrote right here. And let's see, I'm going to think of P as being half the distance in the midpoint here to the axis of revolution. So there's the P that I drew right there. And then I have the height of this rectangle, which is actually sitting right here. Now I'm going to add a couple more axes. If I go from the center or the point of the revolution, or the axis of revolution, which is the center of this ring, out to the outer ring, that I can think of as being this distance P, which is from the axis of revolution to halfway through this width of the ring plus the other half of the ring. And if I go just to the inner ring, I can do the same sort of a thing. I can think of that as P minus W over 2. Now this is actually two different radiuses. I can think of this one as being the outer radius, and this as being the inner radius. So keeping this in mind, I can find the volume, to find the volume of the shell, I'm going to consider the inner and outer radius. If P is the center, then the inner radius is, just like I wrote here, this inner radius is P minus W over 2. And the outer radius is P plus W over 2. So the volume of the shell is then pi, it's pi r squared, where this is the outer radius, minus pi r squared, where this is the inner radius. And this is a little bit misleading. If I take this whole thing and multiply it by h, then do a little algebra and you will get 2 pi times p times w times h. This h, I guess if we change positions there, it'll make a little bit more sense in terms of algebraically how we came about it. Now what this amounts to is 2 pi times the average radius, which I'm thinking of as being p, times the height, which is h, times the thickness, which is w. Now I'm avoiding delta y's and delta x's because I really haven't talked about which radius or which axes specifically we're going to be going about. But if we think of this still kind of generically at this point, I'm going to say the change in volume, because if one of these shells, let's go back here for a second, see, I'm going to constantly change the shell. This rectangle is going to move over as I change x, or if I was going around the if I was going around the x-axis, then it'd be changing as I change y. The change of volume, delta v, I can represent as 2 pi times, right now I'm going to use functions of y, and I'll specify in a moment how to figure out which way we're actually revolving and whether it's a function of y and whether it's a function of x. But right now, just for notation, I'm going to use 2y times p of y, that's this average radius, or the radius as a function of y, times h of y, that's the height of that rectangle as a function of y, times delta y. The total volume is then approximated by the sum as I equals 1 to n of p of yi, h of yi, delta y, because all these i's are going to be changing as I'm moving this shell, this rectangular piece, across this solid. Now, if I take this thing in the limit, then what I end up with is an integral, which is 2 pi times the integral from c to d of p of y times h of y dy. That's my volume. So the whole point behind all this is kind of just to develop the idea is if I'm revolving around the y-axis here, I have this representative rectangle that I'm actually taking this rectangle and spinning it around, and I get this. And this rectangle I move, so the heights could be changing as a function here, in this case x. And I can think of this by breaking it down and using the inner and outer radiuses to actually figure out the volume of this individual shell is. So now that I've come up with this specific equation or formula, if you want to look at it that way, to find the volume using the shell method, what I really want to do is think in terms of how this is going to look if I have a horizontal versus a vertical axis of revolution. Now this is actually a horizontal axis of resolution, or revolution.